All right, we're going to start chapter 7, which is about confidence intervals and sample size. And we're going to look at first, we're just going to do 7.1 and 7.2 from this chapter. So this video is on 7.1. And the first thing we're going to look at is, again, the confidence intervals for the mean when sigma is known, or when the standard population standard deviation is known. And so this covers objectives 1 and 2. Find the confidence interval for the mean when the sigma is known, and determine the minimum sample size for finding a confidence interval for the mean. And that objective we will not end up covering. So there's some things we need to know. A point estimate is a specific numerical value estimate of a parameter. The best point estimate of the population mean, mu, is the sample mean, x bar. Okay, so really we're going to be looking at estimating, again, the mu with an x bar. So that's one thing we need to talk about. Then we talk about good estimators. Sample measures are used to estimate population measures. That's something that's done in statistics a lot. And the sample mean is a good estimator of the population mean. But the way we determine whether it's a good estimator, what are properties of a good estimator, is that it's unbiased, that the expected value or the mean of the estimates obtained from samples of a given sample size is the same or is equal to the parameter that's being estimated. Now, you know, I might ask you on the quizzes some of these definitions and some of these properties, but it's really for working the problems. You don't necessarily need to know these, but I'm going to go through them. Anyway, the second property of a good estimator is that it's consistent. So as the sample size increases, the value of the estimator approaches the value of the parameter estimated. So, in other words, really the bigger the sample size, usually the better estimator it is. But it's pretty consistent. It's not gonna vary much with sample size. And it should be relatively efficient. All of the statistics that can be used to estimate a parameter, this estimator, the good estimator, has the smallest variance for all those statistics. Okay, so those are the three properties of a good estimator. Now, confidence intervals for the mean when the sigma is known. We have an interval estimate of a parameter. That's an interval or range of values used to estimate the parameter. And the estimate may or may not contain the value of the parameter being estimated. That sounds really hard. But really, confidence intervals, what that says is within a certain range, we're somewhat confident that our parameter falls within that range. Okay, it may not. Say if we're 95% confident, we're pretty sure it's going to fall in that range, but there's the chance, 5% chance, that it's not going to. And so that's kind of what a confidence interval states. Confidence level of an interval estimate. It's a probability that the interval estimate will contain the parameter. So there's a probability that it does fall within that range that we feel that should fall in. And we have to assume that a large number of samples are selected and the estimation process, is repeated. A confidence interval is a specific interval estimate of a parameter determined by using data obtained from a sample and by using the specific confidence level of the estimate. Now again, all these are wordy definitions. Again, when we get down to doing the problems, hopefully you'll understand a little better what we mean by these terms. But these are the definitions. So this is the meat and potatoes right here. The formula for the confidence interval for the mean of a specific, for the mean, formula for the confidence interval of the mean for a specific A. And so our mean is in the middle right here. And we're looking to be to the left. We have x bar minus this z calculation, and x bar plus that z calculation. So that's our average minus. So that's what gives us the range. And our mu, our population mean, is somewhere between the low end and the high end of this range. Now, for a 90%, you need to remember these. So these are important for you to remember. For a 90% confidence interval, z of alpha, oh, that's really alpha, alpha over 2 is 1.65. For a 95% confidence interval, it's 1.96. And for a 99% confidence interval, it's 2.58. And so those are the z values you're going to use right here and here. Okay? Depending on what size confidence interval is stated in the problem. Okay. So let's go on. Let's see, I think I have to exit the drawing mode. The maximum error of the estimate. Maximum error of the estimate is the maximum likely difference between the point estimate of a parameter and the actual value of the parameter. Okay, so the maximum error of the estimate is the E. And again, whoops, let me go back. The maximum value error is the E. And then we look at these are the numbers we saw on the previous page for the difference confidence intervals, and then we'll have our sigma over the square root of n, which is the standard deviation of the population, over the sample size. So, you know, this one again is the standard deviation, and this is the square root of n is the sample size. Okay, and this is the population standard deviation. Okay. All right, so that's the maximum error of the estimate. So let's go on to the next page and just all right, so the confidence interval for the mean. When we look at the rounding rule, when you're computing a confidence interval using raw data, and that's when you'll use the 1-bar stats on your calculator like the video I made for you earlier. Round off to one more decimal place than the number of decimal places in your original data. So that's something you want to remember when you use raw data. Round off to one more decimal place than the number of decimals in the original data. And when you're computing a confidence interval by using the sample mean with the standard deviation, you round off to the same number of decimal places that you're given in the original problem. Okay. Now, here's some problems. First one is from page 360. Days to sell an Aveo. A researcher wishes to estimate the number of days it takes an automobile dealer to sell a Chevrolet Aveo. A sample of 50 cars. So here's your N, right? There's your N is 50. Right there. We had a mean time on the dealer's lot of 54 days. So let's just list off on the side what we've got. Our N is 50. Okay, the X bar is 54. The population standard deviation is 6. Again, it says, so that's a sigma, is 6.0. And we're looking for a 95% confidence interval. So remember, for a 95% confidence interval, the z we need is 1.96. And that's from that slide we saw before. And then we're just going to plug these things in to our formula and get our numbers that we need for our range. So as we go to the next slide, it shows as we put these in the formula, and here's the data listed up here that we just listed, right here, okay? We put those numbers in and we get a range between, that mu was going to fall between 52 and 56 days. And you need usually a sentence to summarize what you've got. One can say with 95% confidence that the interval between 52 and 56 contains the population mean based on a sample of 50 cars. So, now let's look at this example, waiting times. Let's go ahead and list for ourselves, before we go on to the next slide, the information that we've got. You've got 30 emergency room patients, so that's your N. Okay. So N is 30. The average waiting time for treatment was 174.3 minutes, so that's your X bar. Okay. The population standard deviation is 46.5, so there's our sigma. Again, we know sigma. And we want a 99% confidence interval, which if you remember or you look back on your other slide or in your book, that confidence interval is going to be for that, z is equal to 2.58. And that's your z of alpha over 2. When I say the z, and I wrote 50, I said, hopefully I said 58. Let me get it. There we go, 2.58. All right, so that's a list, and that's a good thing to do. List what you know, and then go ahead and put it back in the formula. So as we go forward then to the next slide, you can see that it's been put in the formula, and we come up with this range of data here, 152.4. Okay, I've been interrupted a couple times, so if the video sounds like it's kind of off, that's why. All right, one can be 99% confident that the mean waiting time for emergency room treatment is between 152.4 and 196.2 minutes. And so that's these, again, these confidence intervals say that mean is going to fall in that range. All right, so as we go forward, here we have a drawing of the 95% confidence interval for sample means. This says that it falls within 1.96 standard deviations of the population mean. This is also if the sample size is 30 or more, or if the sigma is known. When n is less than 30, then we have to do something else. So this, in this part, you're looking for sample sizes of 30 or more plus or the confidence interval. Now these graphs, these show some X bars. That's what these dots are, X bars. You see one here fell outside. The one up there at the top fell outside the range that we find, but not most of them. Most of them fall within that range that we discover. And here's another one, can be 95% confident than an interval built around a specific sample. Mean would contain the population mean. This is the interval about the sample mean. The little bar, the bar you see, vertical bars, and the mean is actually in the middle. It's pretty much the same drawing, but they've drawn the bars with it to show that, and you can still see that that 1 is slightly outside the confidence interval. I'm not going to ask you to draw these kind of graphs on the test, so, you know. All right, so here's where the idea comes from, that you have your alpha over 2, and 90, it says find z of alpha over 2 for 98%. So as you can see, when you look in here, 98% of your data is in this part right here. Okay, 98% of your data falls in there. So what you have then, you have 0.02 or 2% of your data that's in each little tail here. So that's why it's z of alpha over 2. So this is your alpha. So alpha over 2 is 0.01, which means that that's what's here in each of these tails. Okay, that you don't get included, and that's a 98% confidence, because the area under the curve, this range goes from, the range we're looking for goes from here, all of this in here, including, that's the range where you're 98% confident that your mean's going to be in that spot. And that is most of the curve. You're pretty darn confident that your mean's going to fall in there somewhere. So that's how you're going to count. If you need to find the z-score for a certain confidence interval, we know 90, 95, and 99. This is said, what if we want to know 98 or 96 or something that's different? And the way you find the z-score is, again, you figure out what's in the middle, which is your 0.98. What's outside, then, is 0.02, because there's 100% under the whole thing. You divide it by 2, and that's what's in each tail. Now remember, what we list is, you could find the negative z-score. They found the positive z-score. So if I say 1 minus 0.01, then it's 99.01 is the area under the curve. Okay, so anyway, so we go in just like we did before, and you look for the area right here inside the table, the z-table, and then you read to the left and up to find your score. So for 98% confidence, it's 2.33, which makes sense. I mean, it should be between the 95% level and the 99% level. So if you were off, you know, you at least have some guidelines to help you know where you are. If it's not between, in this case, 1.96 and 2.58, well, you'd know you made a mistake in the way you calculated it or figured it out, read it. Okay, so let's go to the next one. 7.3, page 362, confidence intervals and sample size. Now this is data you're going to put in your 1-var stats. You're going to put it in, and I remember I gave you I always put them in list 1 rather than the other list, because then you have to name the list that it's in when you do your 1-var stats. But if you don't remember how to do it or don't know how to do it, it is on, there's a video under chapter notes that shows you how to do these 1-var stats. So this is a lot of data. It's 30 credit unions in southwestern Pennsylvania, and they want the 90% confidence interval. And you can do this by hand, but you know, if you do it by hand, your results could be a little different. And even with different calculators, sometimes it can be different because of the way things are rounded. But go ahead and use your calculator, because I'm going to take that into account. find the mean and standard deviation using technology. And I did not see these, unfortunately, to fix them in the presentation. So let's see what that is. Find the mean standard deviation for the data. We find that X bar is 11.091. The standard deviation S, this should be, let's see if I can cover this up and write it in by hand. I might be able to. Let's see if we can cover this up. Yeah, so do that, and then I'll write it in by hand. What that should say is that S equals 14.405. Okay, so now we've got step 2. We know that the 90% confidence interval, we've got 90% under here, under the curve right here. We've got 0.1 then is alpha. So alpha over 2 on each side here is 0.05. Okay. So what they're going to do then, we find alpha over 2 is 0.05. Find the z alpha over 2. And we find that z alpha over 2 is 1.645, and we're going to say it's 1.65. Now, we already did that. Okay, we already did that in our data, and this table looks like it's off to me, and that's why I'm sort of hesitating. I didn't view this, but I believe you should find that when you go in and look up your area under the curve right here, this should be 0.95, right? Because you only have 0.05 here. So what you should be looking up is 0.95. So I believe this number should actually be in here. And then you're going to look at, I didn't see these typos, unfortunately, before I viewed this PowerPoint. So anyway, then you're going to look to the left and up, and it should all be shifted down. And it's going to end up being 1.65. Actually, what should be shifted down, I think what really should happen is that this whole box is shifted down to cover this. And so we're reading really across here. Okay, so maybe let's just make that look a little better. Again, so that we're not too confused, which it's easy for me to get confused. Okay, so we'll make it red since it was red on the original. So this is where our box should be, and it's going to come out like this. Okay, so you have 1.65 basically is your Z that you're looking for 90%. Now we already really knew that, but that shows you how you can go about getting it. Now we want to know our range, our confidence interval, our 90. What are the numbers that give us the 90% confidence interval? So we'll go on for step 4 and calculate, which we do in this block. And we again substitute. We're using the formula that we're used to using now, hopefully, right here. Okay, we're using that formula, putting those numbers that we found in. This is our X bar, the 11.091. This is our Z that we discovered. Our sigma over the sample size, square root of the sample size. That's subtracted from our mean. Over here, it's added to our mean on the right of mu. So we get our range down here. 6.752 is less than mu, which is less than 15.43. So your statement at the end, one can be 90% confident that the population mean of the assets of all credit unions is between 6.752 million and 15.430 million based on a sample of 30 credit unions. And remember, our sample size has to be 30 or more if we don't know the sigma. We did know the sigma in this one, but it's good still to have the larger sample size. Okay, so let's go on. This is just a technology note that we will be using our calculators to get raw data like this using the 1-bar stats. And you, again, like I said before, you can get some differences in decimal place, some variations in computation just because of the rounding that takes place within the calculators as they do their job or do the calculation for us. All right, here's the formula for the minimum sample size needed for an interval estimate of the population mean. Again, we know sigma. So n is the sample size that we need. E is the margin of error. We had that calculation before, and this is using it for the sample size. So this is one that you need to memorize. You know, it'll probably ask you for it in a quiz, and you need to memorize it. Now, I probably on the last test am going to give you some matching at the beginning of the test that will, so all the correct formulas will be there on the test, but you have to know which is which. So you don't have to necessarily be able to reproduce them, but you need to be able to identify them so that when you take your last test, you have the correct formulas identified so then you can apply them and use them. And your last test, just while I have you here, is not comprehensive. It is just over the last chapters. It is just another unit test or chapter test over what we've covered since the last test. Okay, so if there's any fraction, this is important, if there's any fraction or decimal portion in the answer, go up to the next whole number. Because you don't want to, if you go below it, then you're under the sample size that you need. So you want to always round up for sample size. All right, so a scientist wishes to estimate the average depth of a river. He wants a 99% confidence that the estimate is accurate within 2 feet. From a previous study, the standard deviation of the depths measured was 4.33 feet. How large a sample is required? So we have, this is our information listed. We want Z is 99% confidence, so Z is 2.58. He wants to be accurate within 2 feet, so his error, his E, is 2 feet. And the sigma is 4.3 feet. Now, be careful and make sure that units agree in something like this. In any problem, really. I'm not going to try to trick you in that way, but occasionally you might run into a problem in a book where the units do not agree. So kind of notice your units to make sure that you don't need to change one to a different, like if one was given in inches and one was given in feet, they need to be the same. So here's our calculation. We put these things in our formula right here. You square it. Once you do the calculation inside the parentheses first, and then you square it. Okay, so be sure that you remember you do this first and then you square it. So you get 31.2, and again you round up because 31 would be too little. We need a minimum of 31.2 sample size. So 31 is underneath that. So you've got to round up so you know it includes that it's more than. You'd rather be on the safe side on a sample size. So you have to have at least a sample of 32 measurements in order to be confident that your estimate is a good one. Okay, and the next will be 7.2, so we'll stop here and I'll have another video with 7.2.